So in this video, we're going to talk about how to graph rational functions. So rational functions are the ratio of two polynomials. So the examples f of x and g of x are two rational functions. So here is the rational parent function. So this is its graph. It's described by the equation f of x equals 1 over x. So when we talk about all other rational functions, they'll have the form f of x equals a over x minus h plus k, where a, h, and k are going to be constants. So those are going to be represented by different numbers depending on the type of rational function that we have. So when we talk about graphs of rational functions, we're going to describe some key characteristics. We're going to be talking about the domain and range, the asymptotes, and the zeros of the function. So let's start off by talking about the domain and range of a rational function. So just like with radical functions, graphs of rational functions are going to have domain restrictions. So if we look at this example, we have the graph of f of x equals 1 over x minus 2 plus 5. Notice that all x values are not included in the domain of my function, right? You can see here I have this gap where my function kind of jumps from one piece to the next. So that's telling me that there are some x values that may not be included in the domain. So why do you think we would have a situation where some x values are not included in the domain? Look at this function for a minute and think about what x values would not make sense in the context of the problem. So did you think about it? So the reason is because notice I have a fraction, right? So when we talk about rational functions, we're going to see fractions in our equation. And so remember, when we have a fraction, you cannot have 0 in the denominator, okay? So this x minus 2, that cannot be equal to 0. So that's why we have that exception in our domain, right? Because remember, you can't have 1 over 0. That is undefined, okay? So that's what gives us this exception when we're talking about rational functions. So if x minus 2 is equal to 0, let's see what x value that would be, right? If I have x minus 2 equals 0, if I add 2 to both sides, that's going to give me x equals 2. Okay, so that is a value that will not be included in my domain. So that is why I have a domain restriction when I talk about a rational function. So let's describe the domain of this function. So we've already figured out that x cannot equal 2, right? So because we don't want to have that 0 in the denominator, so we've said that x cannot equals 2. But notice that all other values are included in the domain, right? We just have this little jump right here at x equals 2. So the way we would describe that is we would say, okay, well, all values from negative infinity up until 2 are included, okay? 2 is not included, so I'm going to need to use that open parentheses. And then I'm going to write the union symbol, okay, because there are two pieces of this domain. Since the domain is not continuous, I'm going to have to describe it like this is going to be piece 1, and then this is going to be piece 2, okay? So that's what I use the union symbol for. The union's like saying and. So then the other piece of the domain is going to go from 2 to positive infinity, okay? So that's how you would describe the domain of this rational function. So this is just basically another way of saying all real numbers except x equals 2. Okay, so what if we describe the range? Okay, so let's think about the range of this rational function. So notice that if I'm looking at the y values, okay, so now going up and down, so it includes the y values up to here, and then my function sort of jumps, and then I have y values going from this direction, okay? So notice that the y value of 5 is not included. Well, why is that? Well, let's think about this. For this function to be equal to 5, right, I would need this to equal 0, okay? But I can't ever have that. So like if I have 1 over x minus 2, that's never going to equal 0, right? Because if I try to simplify this, like if I try to do like crisscross multiply, I'll get like 0 equals 1 times 1, which is 1. That doesn't make any sense. So this does not equal 0. So that's why f of x cannot equal 5. Okay, because if this was 0, I'd have 0 plus 5, which equals 5. So f of x does not equal 5. So that's why my range also has that jump in it. So if I was describing the range, I'm going to use a similar method to when I described the domain. I'm going to say it's going to go from negative infinity to 5, not include 5. And then I use the union symbol for the second piece. And then I say 5 to positive infinity, okay? So those are the two pieces of my range. So for a rational function in the form a over x minus h plus k, the values of h and k are going to help us figure out the domain and range. The domain is going to go from negative infinity to h, and then from h to infinity, right? That makes sense because h is the value that's going to make the denominator equal to 0. The range is going to go from negative infinity to k, and then from k to positive infinity. Okay, that makes sense because to get the f of x equals k, a over x minus h would have to equal 0. So since it cannot equal 0, that's why the range only goes up to k, and then from k to infinity. So we also have this idea of something called an asymptote in a graph of a rational function. Okay, so it's really important to understand that asymptotes are not like on the graph. So if you go to Desmos or if you go to your graphing calculator and you type in the equation of a rational function, it won't graph the asymptote. But asymptotes are lines that we know that are there because we know how the function looks like. Okay, so what they are lines that the graph will approach but not actually cross. So rational functions can have vertical and or horizontal asymptotes. So let me show you what they look like. So if we talk about this function, we would say it has a vertical asymptote right here, okay? Because you see, if I draw in this line, okay, through x equals 2, notice that my graph is going to get really, really, really close to 2, but it's not actually going to cross it, okay? So that x equals 2 is sort of like a boundary line, right? And so that's the asymptote. So we would say that x equals 2 is a vertical asymptote. It's a line that's not already on my function. I can just draw it in and then say that, my graph is going to get really, really close to it, but not actually cross. If you're looking at the equation, you can find the vertical asymptote by setting the denominator equal to 0. So if I say x minus 2 equals 0, and then I solve for x, notice that that will also give me x equals 2. Okay, so horizontal asymptotes. Horizontal asymptotes will be based on the end behavior of the function. Okay, so remember the end behavior, we say what happens as the function goes on forever, right? What happens as x approaches negative infinity, and what happens as x approaches positive infinity? Well, as x approaches negative infinity, let's think about what's happening to our function. What value does it get really, really close to? Notice that it approaches 5, but it doesn't ever actually equal 5. And then look, as we go to positive infinity, notice that the same thing is happening, right? So here's my graph going to positive infinity. Notice that it's going to get really, really close to 5, but it's not actually going to equal 5. Okay, so that's why we have a horizontal asymptote at y equals 5. So that means if I draw in the line, okay, remember y equals 5 is the equation of a horizontal line. If I draw in that line at y equals 5, my graph is going to get really, really close to it, but it's not actually going to cross it. Okay, so that is called a horizontal asymptote. So for rational functions, if they're in the form f of x equals a over x minus h plus k, the vertical asymptote is going to be given by x equals h. Okay, so x is going to equal that number that's right here in the denominator. And then the horizontal asymptote is always going to be y equals k. So we can also talk about what are the zeros of a function. Okay, so remember we can find the zeros of a function by setting the function equal to 0 and then solving for x. So it's important to note that not all rational functions will have zeros. So for example, if we want to find the zeros of the function f of x equals 1 over x minus 2 plus 5 that we've been working with, we would set the function equal to 0. So let's set it equal to 0. So we have 0 equals 1 over x minus 2 plus 5. So now we need to solve this equation for x. So to solve for x, I'm going to start off by subtracting 5 from both sides. So when I do that, I get negative 5 equals 1 over x minus 2. Well, so now I need to solve this problem, right? So to solve this, I'm going to turn this negative 5 into a fraction. That's going to be negative 5 over 1. And then I'm going to do crisscross multiply to simplify this expression. So on the left, that gives me 1 times 1, which is 1. And then I have that equals negative 5 times x minus 2. So I'm going to continue working on this problem. So I have 1 equals negative 5 times x minus 2. So I'm going to start off by distributing that negative 5. And I have 1 equals negative 5x minus negative 5 times 2. So I have 1 equals negative 5x plus 10. So now I'm going to subtract 10 from both sides. And when I do that, I get negative 9 equals negative 5x. And then I divide both sides by negative 5. And that gives me 9 over 5 equals x. So 9 over 5 equals x. Remember, the zeros will also tell you the x-intercepts. So that means that this graph is going to have an x-intercept at 9 over 5, comma 0. So notice how the zeros relate to the graph. So we said that it has a 0 at 9 over 5. So notice that right here, if I look at the graph of this function, notice that right here at 9 over 5, which if you convert that to a decimal, that is about 1.8. You can see that it does have an x-intercept there. Okay, so zeros will tell you the location of the x-intercepts. That's why it's important to help find the zeros. Okay, so for a rational function in the form f of x equals a over x minus h plus k, the zeros can be found by setting the function equal to 0 and solving for x as long as k does not equal 0. If k equals 0, the function will not have any zeros. So remember, I told you there are some rational functions that won't have zeros, so that means they won't have any x-intercepts. That means that those graphs will never cross the x-axis. So these are the steps to graphing rational functions. You're going to start off by determining the asymptotes, then creating a table of values surrounding the vertical asymptote. Then we're going to plot the asymptotes and the points in the table, determine the domain and range, determine any zeros, and then graph the function. So let's tie everything that we've been talking about all together, and let's work on graphing this function. F of x equals 1 over x plus 3. I'm just going to remind you of general form so that we know what the values of a, h, and k are. So remember, general form is a over x minus h plus k. So if I was going to identify from this function, I would say that a equals 1. H, well, notice that it is a minus h in the general form, and then this gives me a plus 3. So that means that h is actually negative 3. Okay, because I would have to have x minus negative 3 in order to get the x plus 3. Okay, so h is negative 3. And notice that I have no term being added here, right? So this is like a plus 0, so I would say that my k equals 0. So let's figure out the asymptotes. So you can use the definitions or you can use the equation to figure out the asymptotes. Remember, the vertical asymptote is going to be determined by setting the denominator equal to 0, or you can say x equals h. Either way is fine. So we just say x plus 3 equals 0, which gives us x equals negative 3. That's the vertical asymptote. The horizontal asymptote is going to be given by y equals k. In this case, y equals 0. And so now let's work on creating our table of values. So what we're going to do is, like, see here, negative 3 is the vertical asymptote. So we're going to figure out the values of some points that are around the vertical asymptote so that we can create the graph of our function. So we have f of x equals 1 over x plus 3. So notice here is negative 3. So we know that at this point, f of x is undefined. That's our vertical asymptote. So let's look at a few points on either side of that value. So let's start off with negative 6. So we have f of negative 6, which is 1 over negative 6 plus 3. So that's 1 over negative 3, negative 1/3. And then we have f of negative 5, 1 over negative 5 plus 3. So that's 1 over negative 2. We have f of negative 4, 1 over negative 4 plus 3. So negative 1. Now let's go to negative 2. So we have f of negative 2, 1 over negative 2 plus 3. So that's 1 over 1, which is 1. And then we have f of negative 1. So 1 over negative 1 plus 3. So 1 over 2. And then finally we have f of 0. So 1 over 0 plus 3, which is 1 over 3. So now what we're going to do is we're going to go to our coordinate grid and we're going to graph all of these points that we have. So let's go ahead and graph these on our function. So we have, let's see, negative 6, negative 1/3. So about here. negative 5, negative 1/2, negative 4, negative 1. And then so we have the asymptote at negative 3. So I'm just going to draw in that dotted line. I know the asymptote is not technically part of the graph, but I'm just going to draw it so I know why my points kind of change. And then I have negative 2, 1. I have negative 1, 1/2. And finally, I have 0 and 1/3. Okay, so now we need to figure out the rest of this graph. So we've created, determine the asymptotes. We also have an asymptote, remember, our horizontal asymptote at y equals 0. So I'm going to go ahead and draw in a dotted line for that. So I know that this function is never going to cross the x-axis. So here I have my horizontal asymptote, and this is my vertical asymptote. We've created our table of values, plotted the asymptotes and the points. Now let's figure out the domain and range. Okay, so we know the domain, we know that the value of h is negative 3, and we know that the value of k is 0. So from those definitions that we had, we know that the domain is going to go from negative infinity to negative 3, and it's going to go from negative 3 to positive infinity. The range is going to go from negative infinity to 0, and it's going to go from 0 to positive infinity. Okay, so now let's determine any zeros of the function. Okay, remember, to determine zeros, we need to set the function equal to 0 and solve for x. So we have 0 equals 1 over x plus 3. If we crisscross multiply, we end up with 1 equals 0 times x plus 3, which tells us that 1 equals 0, and that does not make any sense. So it has no zeros. Okay, so we'll have no x-intercepts. So let's use all this information to go ahead and draw in our graph. So we know that it's going to get really, really close to y equals 0 and not equal it. And it's going to also get close to x equals negative 3 and not equal it. So this is this piece of the function. And then I'm going to draw in my other curve. So we're going to use the asymptotes and the points that we plotted to generate the graph. Okay? Remember, the horizontal asymptote tells you the end behavior. So I know it's going to get close to 0 as it tends to positive and negative infinity. And then I also know that it's going to approach negative 3, x equals negative 3, but never actually equal it. Okay, so now let's go ahead and graph the function f of x equals 1 over x minus 2 minus 3. Okay, so we're going to use the same strategy as before. So let's go ahead and just remember general form. So this is a over x minus h plus k. So we know that h equals 2. And then in this case, notice we do have k. K equals negative 3. So let's determine the asymptote. So the vertical asymptote is going to be x equals h. So that's x equals 2. The horizontal asymptote is going to be y equals k. So we have y equals negative 3. So we're going to create a table of values around the vertical asymptote at x equals 2. So here I have my table. So we know at x equals 2, our graph is undefined. So let's plug in these values that are around that point. So if we plug in negative 1, we have f of negative 1 is 1 over negative 1 minus 2 minus 3. So that's 1 over negative 3 minus 3. So that is negative 3 and 1/3. And then now let's plug in 0. So we have f of 0 equals 1 over 0 minus 2 minus 3. So that is 1 over negative 2 minus 3. So that's negative 3.5. And then we have f of 1, which is 1 over 1 minus 2 minus 3. So that's negative 1 minus 3. So that will be negative 4. And then now let's plug in the values on the other side. So we have f of 3. So that will be 1 over 3 minus 2 minus 3. So that's 1 over 1 minus 3, which is 1 minus 3. So that's negative 2. Then we have f of 4, which is 1 over 4 minus 2 minus 3. So that's 1/2 minus 3. So if we have 1/2 minus 3, that is negative 2.5. And then finally we have f of 5, so 1 over 5 minus 2 minus 3. So that's 1 over 3 minus 3. So we have 1 over 3 minus 3. And that gives us -2 and 2/3. So if we go ahead and graph these points now, so we have -1, -3, and 1/3. So that goes here. And then we have 0, -3.5. And then we have 1, -4. And we have 2. Okay, so 2 is where we have our vertical asymptote. So I'm going to go ahead and draw that in. And then we have 3, -2. 4, -2.5. And then 5, -2 and 2/3. Okay, so let's go ahead and graph in our other asymptote. So we plotted the vertical asymptote. Let's also do the horizontal asymptote. So that's at y equals -3. So I'm just going to sketch in that horizontal asymptote. And I'm just going to label it so that you know there's horizontal asymptote, vertical asymptote. So we've done the asymptotes, the table, and then let's figure out the domain and range. So remember, the domain is going to go up to the value of h. So we're going to have the domain, so -infinity to 2, union 2 to positive infinity. The range is going to go to the value of k. So we have -infinity to -3, union -3 to infinity. So now let's go ahead and connect the points and form the graph of our function. So we know it's going to get close to the vertical and horizontal asymptotes, but never actually cross. So this is how you draw in the two pieces of this rational function. Oh, and also let's determine any zeros. Okay, so the zeros of this function, if we figure those out, we're going to set the function equal to 0. So we have 0 equals 1 over x minus 2 minus 3. So now to solve this function for x, we're going to add 3 to both sides. When we add 3 to both sides, we get 3 equals 1 over x minus 2. I'm going to turn this into a fraction so I can crisscross multiply. So we have 1 equals 3 times x minus 2. And if we go ahead and simplify this, we have 1 equals 3x minus 6. So we're going to add 6 to both sides. We have 7 equals 3x. Divide both sides by 3. So we have 7 over 3 equals x. So 7 over 3 is about 2.3. So that means we'll have a x-intercept at 2 1/3, 0. So if we go to our graph, we can see that at 2 1/3, we do have an intercept. Okay, so now let's go ahead and graph the function f of x equals -2 over x plus 4. Okay, so once again, I'm going to compare that to my general form. So f of x equals a over x minus h plus k. So in this case, there's nothing being subtracted from h. Okay, so I'm going to say that h equals 0. And then my k is going to be 4, right? Because I have that plus 4. So my vertical asymptote is going to be at x equals 0. And my horizontal asymptote is going to be at y equals 4. So we're going to create a table of values around x equals 0 to figure out the points that are on this function. So at x equals 0, I know that my function is going to be undefined. Now let's figure out these other points. So I have f of -3. So I have -2 over -3 plus 4. So that is going to give me 2/3 plus 4. So that is going to be 4 2/3. Then I have f of -2. So that's -2 over -2 plus 4, which is 1 plus 4, which is 5. So I have f of -1. So that's -2 over -1 plus 4, which is 2 plus 4. So that equals 6. I have f of 1, which is -2 over 1 plus 4. So that's -2 plus 4, which equals 2. I have f of 2, which is -2 over 2 plus 4. So that's -1 plus 4, which is 3. And then I have f of 3, which is -2 over 3 plus 4. So if I do 4 plus negative 2 over 3. That gives me 3 and 1/3. So now I'm going to go ahead and fill in the graph of this function. Okay, so we need the asymptotes. So remember we said we had a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 4. So I'm going to go ahead and graph those lines. So I have x equals 0. So here is my vertical asymptote. Y equals 4 is here. So there is my horizontal asymptote. So now let's plot in the points from our table of values. So we have negative 3, 4 and 2/3. Then we have negative 2, 5. And then negative 1, 6. We have 1, 2, 2, 3. And then 3, 3 and 1/3. So we have the asymptotes, we have our points. Let's talk about the domain and range. So the domain is going to go from negative infinity to 0, right? The value of h, and then 0 to infinity. The range is going to go to k. So we have negative infinity to 4, and then 4 to infinity. Now let's figure out any zeros of this function. So we set this function equal to 0. So we have 0 equals negative 2 over x plus 4. We start off by subtracting 4 from both sides. So we have negative 4 equals negative 2 over x. We can turn the 4 into a fraction and then crisscross multiply. So we have negative 2 equals negative 4x. And then we divide both sides by negative 4. Which gives us 1/2 equals x. So that means that I have an x-intercept at 1/2, 0. So I'm going to put my x-intercept right here. And now I can form the graph of my function. So I'm going to connect the points and then show that it's approaching those asymptotes. So this piece and this piece. So there's the graph of f of x equals negative 2 over x plus 4. So now you can go ahead and pause the video and try graphing this function on your own. Okay, so you're going to use the same steps that we've been doing to go ahead and graph this function. Remember, it's always a good idea to compare it to general form so you can figure out the values of h and k. So that gives us that h equals 2 and k equals 1. So that means we have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 1. I created a table of values around x equals 2 because that's our vertical asymptote. And then I found these points that are included in the graph of our function. So then I graphed the vertical and horizontal asymptotes, and then I filled in those points that we had. And then you also want to go ahead and figure out the domain and range. So remember, the domain is going to go from negative infinity to h, and then h to positive infinity. Range is going to go from negative infinity to k, and then k to positive infinity. I found the zeros by setting the function equal to 0, which told me that I have a 0 at x equals 1, so I have an x-intercept at 1, 0. Coincidentally, 1, 0 is also one of the points that we filled in our table, so it was already included in our graph. So that is how you graph rational functions. Remember, to do this, you just basically have to determine the asymptotes. Remember, it's always a good idea to go back and compare to general form. F of x equals a over x minus h plus k. Remember, x equals h will be the vertical asymptote. Y equals k will be the horizontal asymptote. Then you create a table of values surrounding the vertical asymptote to find some more points to fill in on your graph. Then plot the asymptotes and the points in the table. Determine the domain and range. Remember, domain is going to go from negative infinity to h, and then h to positive infinity. Range is going to go from negative infinity to k, and then k to positive infinity. You're going to determine any zeros by setting the function equal to 0 and solving for x. Remember that all rational functions may not necessarily have zeros, and then you finally graph the function.